Sir, are there a lot of forms for the Hamiltonian?
Uh, you mean for a given Lagrangian, the Hamiltonian is fixed, right? Because it's given by the Legendre transformation, right? So suppose you have a Lagrangian, which is a function of the generalized coordinates and the generalized velocities, okay? Then you define the momentum or momenta canonically conjugate to the coordinate qi by this equation, okay? And then you say that, okay, I'm going to define the Hamiltonian to be the Legendre transformation of the Lagrangian, where we replace the generalized coordinates qi dot, the generalized velocities by the generalized momentum. So this is a Legendre transformation. This ensures that h is a function of the pi's and the qi's, right? So once the Lagrangian is given, the Hamiltonian is fixed. Does that answer your question, or was it a different?
Yes, sir, it answers. About the phase space, is it related to the chaos theory because it depends on the initial conditions?
No, phase space is defined for all classical mechanical systems. So phase space is the space of all generalized coordinates and generalized momenta. So, phase space, if your system has, in 3 dimensions, has n degrees of freedom, then your phase space will be 6n dimensional, okay? And because you will have the momentum, and then you will have, you will have the coordinates, right? And the point is that, if you have one point in phase space that describes the system, the state of the particle at a given time t. What the Hamiltonian does is that the Hamiltonian defines a vector field on your phase space, okay? So if this is your phase space, then, if I give you a certain Hamiltonian, what it defines is a vector field. What is a vector field? It's a specification of a vector at every point in your space. So if I give you the state of the system at any given time, which is its momentum and its position, then the Hamiltonian defines the flow of this system. And that's called the Hamiltonian flow. Now, there may be systems, typical systems, where there is no chaos. So what does that mean? That means that, so in a system there is no chaos. Suppose you take the state of the system to be at some point time 1, and you compare that to the state, suppose what happens if the system had a state 2. Now, under this Hamiltonian flow, if the system is not chaotic, then what will happen is that, as they flow, the distance between these 2 points, they may increase, but they won't increase that much. They might increase, in a polynomial fashion. So those are the non-chaotic systems. But chaotic systems are the ones in which, even though the initial points are very close to each other, as time progresses, they separate exponentially, right? So that means that the system is very sensitive to the initial condition. If you change the initial condition slightly, the final condition diverges exponentially fast. And those are the systems which are called chaotic. So phase space has a priori nothing to do with chaos, but if you have a system that is chaotic, then the trajectories under Hamiltonian flow in phase space will have this kind of property. Okay?
Yes, sir. And about the generalized coordinate, is that for the n dimensions? Q1, Q2, Q3.
Right. So suppose you're working in three-dimensional space, right? You may want to work in higher dimension. For example, in string theory, in supergravity, it posits that space-time has more than four dimensions. But in three-dimensional space, if you have a system of, say, n particles, right, then there will be, qi are the coordinates, then there would be 3n components of this generalized coordinates, right? Because each of these coordinates is a vector, so it has 3 components. And similarly, there will be 3 components for the generalized momentum, right? And the phase space treats the momentum and the coordinate symmetrically. And therefore, the dimension of phase space is going to be 6n dimensional, okay? So this 6 has to do with the space-time dimensions and the fact that you have both coordinates and momentum, and this n has to do with the number of particles. So in classical field theory, you have a field. For example, in Maxwell field, you have a field which is a function of space and time. Now, such fields can be thought of as a continuous limit of a generalized coordinate. So in those cases, in field theory, the phase space dimension would be how many dimensions? Can someone tell me?
4n.
So here, it's actually going to be, phase space will be infinite dimensional. Because what's happening here is that in field theory, we go to field theory from classical mechanics to field theory is the field becomes a function of space-time. So this discrete index becomes this continuous index qx, okay? And here it was a function of time. This is still a function of time. Anyway, but that's beside the point. It's outside the scope of this class, so I won't go into that, okay? Okay, any more questions from phase space and stuff? I want to make one more comment, okay? Phase space is, treats the coordinates and momentum kind of symmetrically, right? And, Hamilton's equation is dH by, say, dPi is it minus Qi dot or plus Qi dot? I forget. One of those.
So minus.
Okay, good. Somebody knows. Okay. But this one has plus. So, these equations look very symmetric with each other. And there are transformations between P and Q that do not change the form of these equations, okay? So these equations are equations that leave the form of Hamilton's equation invariant. And these transformations are called symplectic transformations. And there's a whole groups of these transformations called symplectic groups. Right? And when you study classical mechanics, you will learn some of this mathematics, okay? So there's a very beautiful theory where you can change these equations and put them in a form which is more amenable to, say, a solution. Okay, any more questions? at some point you will see that a Hamiltonian formulation of classical mechanics has very deep connections with quantum mechanics. In fact, Heisenberg, who was one of the co-discoverer of quantum mechanics, formulated quantum mechanics in analogy with Hamiltonian mechanics. Okay, so there, and then Dirac came up with a prescription where if I give you any classical system, you can quote unquote quantize that system by using the Dirac prescription. And that's a prescription that is used for many, many quantization processes, even in field theory. Okay, any more questions from previous stuff?
Awesome.